everyone, and welcome to this session on novel routes to polar order. First speaker this morning is James Rondinelli from Northwestern University, and he will tell us about polar oxides beyond perovskites through vacancy and chemical order.
Okay, great. And then can you give me like a 5 minute to at the 20-minute mark? So good morning. I'd like to thank the organizers for giving me the opportunity to tell you a little bit about what we're doing in the discovery of polar oxides, or oxides without inversion symmetry, in a class of materials outside of perovskite. So we heard a lot about perovskite. And I'd also like to thank you for waking up early and attending the lecture. The idea I'm going to describe today is shown in this cartoon here, where what I'm going to show you is that you can combine structural vacancy order, so periodic arrangements of multiple polyhedral units, so these are octahedra and tetrahedra, which exhibit long-range order, with cation chemical order to lift inversion symmetry. This is an alternative complementary route to find crystals without inversion symmetry. And what I'll show you is actually this idea came from attending this workshop in 2014. So I'll show you the abstract which motivated this project that I'm telling you about today. Okay, so this work was performed in my group by two students. One, Joshua Young, who's now graduated. He's a postdoc working, and Youngjin Chin, who's right here. This is Josh. And has been done in collaboration with Steve May at Drexel. So the material I'm going to tell you about has been grown as a thin film, and I'll show you some of those results. And it's been characterized at Penn State through the NSF MRSEC there. They're characterization facilities by Venkat Gopalan and Nassim Alem, performing electron microscopy. And so I wanted to use this for just a quick advertisement. I'm looking to hire a postdoc on any one of these topics. So if you know a student who's going to graduate soon, or you know a postdoc who's looking for another position, please put them in contact with me. And if they're here, I'm happy to chat with them today. I'm around all day. Okay. So the thing we're looking for is a way to lift inversion symmetry. So you're attending the ferroelectrics workshop. Either you're focused on ferroelectrics or materials beyond. And often all of those materials beyond have broken inversion symmetry. And the idea that functionality can arise from lifting parity is a rather old concept. So Pierre Curie told us that it's asymmetries that create phenomena, and we're looking for the loss of inversion symmetry. And some of these effects we've heard about already at the conference, and we'll continue to hear about today and into tomorrow. And as an additional plug, two of my students are attending the meeting. One is giving a talk tomorrow morning on the ability to control the band gap in 1-1 ultra-short period oxide superlattices by Ferroic phase transitions. And my other student is giving a poster this evening on polar metals. So please check out those two talks or posters. So what we're doing is trying to think about ways to lift inversion symmetry. And what I want to do is take a survey of what's possible in terms of crystal chemistry of perovskite-derived structures. So these are structures which exhibit corner-connected octahedra in 2 or 3 dimensions. And so this is a survey of the ICSD back in 2016. And what I'm showing you is the potential landscape of possible compositions that you could have by just ordering different chemical species, maintaining charge neutrality. And so if I go to perovskite, I can put in divalent, trivalent cations, counter charge balancing B-site cations, and I can enumerate something like 400 possible combinations. I can do this for other layered oxides as well. These are the Diab-Jacobson phases. These are the Rudolphin-Popper phases or Avilius phases. And then these are, say, ultra-short period superlattices of perovskite. So you can enumerate these. And then if you compare this to what's been known, and if you think of what has been known lives in the ICSD, this is some small subset of that. Okay, and then if you focus on those compounds which have broken inversion symmetry, and not even just the ones that are polar, just the ones that break inversion symmetry, it's some small fraction of those synthesized compounds. So there is a dearth of materials which have broken inversion symmetry, at least in layered structures like this, in oxides like this. And we can rationalize this based on physics-based models of why this occurs. Well, if you use a traditional mechanism for lifting inversion symmetry, something like the second-order Jahn-Teller effect, you're typically limited to early transition metal chemistries, or chemistries which have lone pair electrons. Okay? The other complication in this factor, and we heard a little bit about this yesterday, is that there are competing distortions in these types of structures which are centrosymmetric. Okay, and these will occur when you have very different ionic sizes for your cations, and these preserve inversion symmetry, and they can compete with those mechanisms which lead to polar displacements and ultimately broken inversion symmetry and perhaps a ferroelectric polarization. So what this talk is really about is how do we circumvent this problem? Okay, and as I mentioned, the idea for this project, or the concepts I'm going to describe today, came from this meeting. It was actually here in this room in 2014. Okay, and there was a presentation by Professor Taniguchi on ferroelectric phase transitions driven by twisting of silicate tetrahedral chains. So he's looking at this bismuth silicate, and I have an SiO4 tetrahedral network which spans the structure. And what he described was experiments which are now published in this journal here prior to the meeting, and electronic structure calculations which really did show that these tetrahedral chains lead to the loss of inversion symmetry in the structure. And so immediately I was like, well, I know many oxides also exhibit tetrahedral chains, but no one ever discusses these types of materials. We sort of are constrained often to perovskite land. And so really what this talk is how do these tetrahedral chains lift inversion symmetry, and can they lift inversion symmetry in perovskite-derived or perovskite-related phases? So this is a good reminder for those in the audience that there are many sort of key little nuggets to take away from many of these presentations. Okay, so are there alternative routes to lift inversion symmetry? And let me give you a little context for this. So what we're doing is trying to look for beyond second-order Jahn-Teller effects, so things outside of chemistry. Can we structurally lift inversion symmetry? And this is also considered an area in chemistry as geometric-driven or accidental ferroelectrics. And we've heard about some of these improper ferroelectrics already at this meeting. And so let me give you a little slant on how I view this. One way we can additionally lift inversion symmetry is through this idea of multi-mode coupling. Okay, and so the idea is that you can have multiple modes, here represented as Q, which are interacting with each other, and in combination, they can lift the necessary symmetries that preserve, say, inversion symmetry. And so these modes can typically be rotations of octahedra, and that's the one I'm going to give you an example of on this slide, or they can be other distortions to the octahedra. They can be first-order Jahn-Teller distortions, things that change the shape of the octahedral unit, or they can be orbital or charge ordering types of distortions, which also change the shape of the octahedra. And so these modes can be any one of these types of distortions I'm depicting for these polyhedral units here. And this was really articulated in a nice series of papers on this compound calcium titanate, this 327 phase, the N=2 member of the Rudolph-Popper family. And it's shown in this diagram here. There's one mode here, which looks like oxygen octahedra tilting about this axis. So if you focus on the red oxide anions, you can see them tilting. Okay, this mode, just like all of general tilt modes by itself, preserves inversion symmetry. Okay, it combines with another type of rotation of octahedra, and it's a rotation along the tetragonal axis. So if you focus on the equatorial oxygens, you can see them moving in or out of phase. Again, an inversion symmetry preserving distortion, but in combination, they break the necessary symmetries for inversion, and they allow polar types of distortions here in the calcium and then in the titanium oxide layers. So ultimately, you do obtain a structure without inversion symmetry, and this material has been known or is referred to now as a type of hybrid improper ferroelectric. Okay, and the idea is quite simple, that you have multiple modes that are coupled to each other, and they interact, and they lift inversion symmetry. Nothing I described here relies on the chemistry other than that the cations are of a particular size to favor these types of centrosymmetric distortions. Tuning the size and the chemistry can increase the polarization, but that's a secondary consideration, at least in my mind at the moment. And so one of the interesting things I was looking at is, how do we discover these materials? And for what it's worth, I looked at citations to articles describing this type of effect. This was late summer, early fall, on rotation-driven or tilt-type ferroelectricity, or this concept of hybrid improper ferroelectricity. And so here it started in 2008, and this is a paper by Matt Dauber and Philippe Gauzet's group, where they looked at 1-1 period lead titanate, strontium titanate superlattices. Here is the example of calcium titanate, where the concept of hybrid improper ferroelectricity was introduced. We contributed to this field by looking at ultra-short period superlattices in 2012. And since then, there's been an explosion in looking, or some sort of explosion in the field at looking at different ways to lift inversion symmetry through these types of nonpolar or interacting modes. This is a paper from Matt Brzezinski's group where they looked at n=2 Rulson-Popper phases, and they induced chemical order to lift inversion symmetry in combination with the rotational modes. And here we're in 2018, and already at this meeting we've seen other ways to apply, say, improper mechanisms to find ferroelectrics. And this gives added functionality. You can look at domain walls and dynamics, I think we'll hear about a little later today. This is the field of, or sort of a snapshot of the field of rotation-driven ferroelectricity. But the manner in which you lift inversion in these perovskite-derived compounds is all the same, and it's going to extend to the route we're going to apply to tetrahedral-containing oxides, or tetrahedral structure-based oxides. And the strategy is shown in this diagram, and it's in a funnel shape because this is the manner in which you can filter away crystal structures which don't, say, satisfy our rules. And the manner in which you design these materials is you start with a centrosymmetric structure without, say, necessary distortions, an idealized case. You identify occupied and unoccupied Wyckoff positions in that space group, so this is just a crystallography problem. And then what you do is add some degree of freedom. So you're going to perturb that ideal structure with some other feature. It can be structural, like a rotation. It could be chemical order. It could be magnetic order, and we heard about that yesterday. Or it could be orbital order, and this is going to have the consequence that it either by itself lifts inversion symmetry or it simply shifts the location of the inversion center in the crystal. And so there will be remaining positions for inversion symmetry, and you add one additional degree of freedom or one additional feature, and that will lift inversion. Okay, this idea of adding order was discussed yesterday in samarium ferrite, where we saw that improper ferroelectricity can be induced by antiferromagnetic domain walls. So that antiferromagnetic ordering was an added feature in the crystal structure that in combination with the structural distortions lifts inversion symmetry. The strategy is all the same. It's just whatever type of order, long-range order, you're most comfortable with. And then with this design strategy, you can find new polar oxides. So this is schematically what's happening. I can demonstrate this for perovskite, where we take an ideal perovskite structure. These are the ABO atoms in the structure. This is the site symmetry on those locations. I can add some order. This is A-site ordering. I shift the position of the inversion centers on the A and B sites. I can try B-site ordering. This also shifts the location of the inversion centers. Then I have an added degree of freedom, say these tilt of octahedra. This is a common tilt pattern in perovskite. You can see it maintains inversion symmetry in the structure. This is the tilt pattern. This is the consequence on the Wyckoff symmetries, site symmetries in the absence of chemical order. And then I just take combinations. And you find, those are what the tilts look like. I take combinations, and I can see, okay, if I have B-site chemical order in, say, a 1-1 period superlattice, this preserves inversion symmetry on the B-site. If I take this tilt pattern, combine it with that one, I lift all inversion centers in the structure, and I have a polar compound. This is nothing about the chemistry. This is purely a crystallography argument. The question is, then, is this phase, can it be made, synthesized? Is it stable? Is it metastable with respect to, say, the unordered phase? And that's a question we can address using computational methods, or if you have a super enthusiastic collaborator who will try to make a lot of materials. Okay, so that's the concept. What I want to do is extend this then beyond perovskites and octahedral rotations and tilts. Can we achieve or use other structural orders to achieve the same effect? And so I like this idea of chemical order. These are these like candy buttons that kids often have. They taste horrible, but they're very nice colors. And what we're going to do is try to induce this effect with anion vacancies. Structural ordered anion vacancies. So these are going to be chemically known compound or equilibrium compounds with long-range anion vacancy order. And so the family we're going to look at is brown millerite. This is its chemical composition, A2B2O5. You can start from perovskite. The prototype structure is this aluminum ferrite. You start from perovskite. You take out 1/6 of the anions. And if you do this in an ordered arrangement, you get the structure of brown millerite. This is alternating planes of octahedra, like this, and tetrahedra, which are linked along this axis. This is the B-axis in the standard setting. If you write the chemical formula relative to perovskite, you see it is oxygen deficient, okay? So you have ordered anion vacancies in this structure. So you can see in terms of the geometry I've shown you, you have oxygen vacancy order in this direction. So I have a plane of oxygen vacancies, fully oxygenated metals, and then another plane and alternating, okay, in this chain-like structure. The other added feature in this structure, which you don't have in perovskite, is that you have different AA distances spanning the different polyhedral units. So this AA distance across from the tetrahedra is much longer than that across from the octahedra. So these A sites are much closer than these ones. In addition, you have displacements within these AO planes like that. Okay? The thing I want to focus on then is this tetrahedral chain. So it's a chain structure into the board. So if I pull out this chain structure of the tetrahedra, I can define an idealized chain where the chain has, say, 180-degree linkages in this direction going into the board. In all of the equilibrium structures, these chains can tilt with a left-handed or right-handed sense. It doesn't really matter which one you define. There's just two types of them. I've colored one blue and one red. And these two-handed tetrahedral chains, when they're rotated, they do have dipoles along the chain direction. Okay? So this local unit, this chain, has a dipole associated with it. Okay? And in Brown-Millerite, the manner in which these chains order determines whether or not the structure has inversion symmetry. That's the key effect. And these symmetries are protected by the glide operations in the space group. So experimentally, there are many, just like perovskite, many compounds which exhibit the Brown-Millerite crystal structure. I'm going to show you some of them on this slide. And I've kept the tetrahedral chain ordering coloring the same so that you can see the difference. There are Brown-Millerite structures which are polar. They look like this. And in those cases, you have a single type of chain. They're either all left-handed or all right-handed in every alternating layer like this. Then there are two other polymorphs which preserve inversion symmetry. And you can think of these as having some, essentially they have a 50% mixture of left-handed and right-handed chains, tetrahedral chains, and they can be exclusively in one layer or the other, or they can be mixed within the layers. And that will dictate whether or not you're in this orthorhombic space group or that orthorhombic space group. Okay. And so there's, in the literature, there's quite a bit of discussion about what types of chemistries favor particular space groups. We looked at this a few years ago in an electronic structures study, and ultimately what ends up is it's a competition between these dipoles, the electrostatic interactions among these dipoles, and an elastic energy that happens when these tetrahedral chains rotate. So the linkage along this direction is through an apical anion like this. As these tetrahedral chains rotate, unlike perovskite, they shear the octahedral layers. They don't keep sort of a rigid type octahedral unit, and that costs elastic energy. And so ultimately the combination or the competition among these types of interactions is what governs the stability. So I don't have time to go into too many details about the stability, but it's in this series of papers here. The added nuance that I just want to mention is that these oxygen vacancies can order in thin film form depending on the strain state. So you can have vacancies, the oxygen vacancy structure ordered in this direction, or it can sit in the plane. And this has been seen experimentally, and one can also probe this computationally. So let me get to some of the results now. So what we've been looking at then are these ferrite compounds for calcium and strontium. And these are the three polymorphs we want to consider. And we've been looking at the energetics, the phase stability of these materials. And so if I take calcium ferrite and perform a density functional theory study, what I find is that the lowest energy phase is this PNAM one. If I look at strontium ferrite, the lowest energy phase is this PBCM one. And so these, the stability of these phases is actually in quite good agreement with the experimental reports. Okay? If you look at the energy scales, you should anticipate that there can be some mixture in a real sample, and this indeed has been observed. And for a long time, it gave quite a bit of confusion to the experimental community about what the real or equilibrium structures are of these two different materials. And so calcium has a smaller tolerance factor. Calcium is just smaller, so you have larger rotations in the structure, just like in perovskite. Okay, so in perovskite, we can lift inversion symmetry through a combination of rotation and tilt, chemical order. In brown millerite, we're going to try the same thing, except it's not really tilting. It's just a combination of static structural units, tetrahedra and octahedra, which have chain-like structures like this, ordered oxygen vacancies. And we're going to have to add some other feature to lift inversion symmetry, or to deterministically lift inversion symmetry. And that, just like in perovskite or these superlattices, will be chemical order. And so you can go through the same exercise that I did for perovskite. Now this is for the brown millerite phase. And you can apply chemical order either on the A site or the B site. You don't really need to study this. The only thing you need to notice is that the number of polar space groups, these ones circled in red, increase, okay, compared to the ones that maintain inversion symmetry. And so what we'll have is this tetrahedral, octahedral network and chemical order, and that will lift inversion symmetry. So structurally, or visually, this is the design strategy. We start from perovskite, we add tilts, we add a tetrahedral, octahedral network, we add chemical order, and we can lift inversion symmetry. Okay. So what we want to do then is look at the stability of these phases from first principles. What I'll consider first, or if we can look at this compound now, calcium, strontium, iron 205. This is going to be a digitally ordered superlattice, if you want to think about it like that. And there are three possible orders. The first one I'm going to show you here is where we have alternating strontium and calcium in every other layer. In analogy to perovskite superlattices, this would be a 1-1 period brown millerite superlattice. Again, the effect of adding the chemical order on the symmetries induced by the tilt or by the tetrahedra and octahedra is to reduce the symmetries to all polar space groups. And what I put in brackets here, the S and the C, corresponds to strontium and calcium here, bridging the octahedral unit like that. So this is a 1-1 period superlattice. We can compute the energetics, and what we predict from first principles is that this phase here, derived from the centrosymmetric one, should be the equilibrium or ground state structure, in close competition to the PC structure. Two other variants that maintain this stoichiometry are these two superlattices here. And you can see in this case, we have two calciums and two strontiums. And those two calciums and strontiums can either bridge the tetrahedra like this, or they can bridge the octahedral units like that. And that's what's indicated by these two lines here. In most of these cases, you find that the number then of polar or structures without inversion symmetry increases. And these are the energetics then of those phases. And so what I want to do is look at in a little more detail this 1-1 period superlattice. It's a little simpler to assess, at least in a presentation. And these are the energetics from the previous slide. In the unordered, the non-chemically ordered structure, we have, again, I remind you, we have two types of A distances. We have short ones and long ones. And these give rise to compensating dipole, layer dipoles. As soon as I chemically order this thing, as you might suspect, calcium and strontium are going to displace by a different amount, and this will lead to a polarization along that B axis in this structure. The added effect of having these tilts or the shearing of the octahedra is I do have iron displacements that occur in the plane. The space group's monoclinic. It provides for a polarization in a direction orthogonal, or not orthogonal, but not along this axis. And I can get a polarization that's quite large due to these tetrahedral chains. So this is iron oxide tetrahedra, which give rise to a polarization. So they're all aligned in this case. And so this is what's predicted from first principles, and we sought out to see, can this be realized in the experiment? And so what was done is that these films were grown by oxide molecular beam epitaxy by Steve May's group, and what we should expect is that this type of orientation for the oxygen vacancies. So Steve May's group at Drexel grew these on strontium titanate substrates. They're coherently strained. They're 35 to 40 nanometer films. He also looked at different periodicities of those superlattices. So in addition to the 1-1 that I just described to you, he looked at a 2-2 and a 6-6 period superlattice. These are 00L truncation rods taken at the APS. For the 1-1 superlattice, you can actually, all of these superlattices, you see the additional Bragg reflection from the brown millerite structure. This occurs at the 003 peak. And then these added satellite features are indicative of chemical order, 2,2 chemical order, 6,6 chemical order. The complication is that the ultra-short period superlattice, the 1,1, the chemical order is induced the chemical order leads to intensities at the same Bragg reflection that gives rise to the brown millerite structure. So it's buried in this reflection. And so then what we did is we went to the group of Nassim Alem at Penn State to look in real space, is there chemical order? And so this is angular dark field STEM imaging of a very large, in a very large field of view of this crystal of strontium ferrite, calcium ferrite. This is the 1,1 period superlattice. And you can indeed see that there is A-site chemical order shown in this projection, so taking slices along this direction. The other thing they looked at is they mapped out locally displacements of both the iron and the A-site cations, strontium and calcium, and fit those displacements to our density functional theory predicted structures and find very good agreement. And in fact, the structure is predicted to have the PC symmetry, so not the one we predicted to be the ground state, but one to be very close in energy with that phase. And so what they looked at and imaged or could plot and track is the displacements of these iron units in the superlattice. And the last thing that I'll show you is that they did indeed confirm the broken inversion symmetry using a seabed technique, so an electron microscopy technique, where they looked for asymmetries or violations of Friedel's rule in the disks that should correspond to the same types of intensities. So this is the experimental intensities, so the 6 bar 00 and the 600. If the structure has inversion symmetries, the intensities should be identical. Here, they're sort of, the contrast is quite opposite. And they perform simulations which mimic this effect. Okay. And so what we find then is one can design or discover new polar oxides outside of perovskite simply by applying a design strategy which combines multiple orders, whether it's structural order, magnetic order, orbital order. It's a general effect. You would need to identify the chemistries compatible with those long-range orders. And I showed you the example then for using tetrahedral and octahedral chains in the structures of brown millerites. So more information can be found in this paper, and the stability of brown millerites in thin film form is described in this paper. And there's many more degrees of freedom in brown millerite than in perovskite. So I'd encourage our thin film growth researchers to think about taking up these compounds. So with that, I'll just conclude and remind you I'm looking for a postdoc, so send them my way. Thank you.
Okay, very nice talk. Questions?
The brown millerite, of course, only the end member. I mean, it's the 2.5 in the perovskite notion. And you have lots and lots of prototypic systems in between, between 2.5 and 3.
Yeah, right.
Do you see any of those?
You mean in the calculation? Have we looked at their energies? Yeah. For this family, we haven't. Those we've looked in the manganites. There is competition between other polymorphs between 2.5 and 3.
I mean, experimentally, the problem is if you make a brown millerite, you find the full whack.
Yes.
You find lots and lots of other phases in between, which are sort of incomplete brown millerite, but they are stable phases.
Yeah, so you performing a traditional solid-state chemistry reaction, you do get this polymorphic competition. In the thin film form, there was no secondary phase of any of these structures seen, and I think that's an epitaxial stabilization effect. But you're right, using traditional solid-state chemistry methods, you do get this polymorphic competition.
I have one other question, if I may. If you measure the dipole moment of these things, but in general, they're appallingly small.
Yeah, the values I showed you here are about 10 microcoulombs per square centimeter, so small, but not, nano.
Not industrial at this point.
Well, I think the challenge here, so most people ask, can this be switched? So maybe that was David's question. So in the calculation, we can map out trajectories which look like these compounds can be switched. In the experiment, it has not been switched yet, and that's still ongoing. So that's kind of the thing we're trying to understand more now.
That was maybe going to be the other half of the question, but I'm actually just confused about the direction of polarization. Can you go back a couple of slides? Yeah. It looks like, I mean, you're talking about polarization along the chains, right?
So in the monoclinic structure, you have an in-plane polarization and an out-of-plane polarization. In the other two structures, it's always orthogonal this way.
Right, but as soon as you put the cation ordering in the vertical direction, like in the first of the three.
So this lifts the mirror plane this way that allows a polarization in that direction.
Okay, so in that case, the polarization is in the layering direction.
Right, because the chains are still 50% left and right, so they cancel.
Okay, so that one looks hard to switch.
These two.
Well, the ones that have polarization in the layering direction, it seems like to switch them.
Yeah, you need to shift the A sites.
You have to shift the oxygens. You know, you have a deficient layer and a non-deficient layer, and you have to shift the oxygens from the non-deficient layer to the deficient layer in order to switch the polarization in that case, right?
Right, which is why I focused on this one, because the component of the polarization we wanted to switch was the one that's not along the long axis.
Okay, now I understand.
Yeah, I didn't make that clear, but you're right.
One more question?
But if you don't have to switch the polarization, you just want a broken inversion symmetry crystal, you're fine.
Just a quick question.
Sure.
Do you know anything about oxygen conductivity in these materials? How easy it is to move these around? Because
I know people have studied them extensively. We haven't looked at that effect. I know they're a family that's well studied for oxygen conductors, oxide anion conductors.
All right, thanks.
Yeah.
Okay, so let's thank the speaker.
You're going to use yours. Did you get a different one?
Our next speaker is Michelle Kotyula from Rutgers University, and she will tell us about the first principle study of ferroelectricity in samarium nickelate with intercalated hydrogen. As soon as the screen will go on. Good.
Great. Okay. Good morning. Thanks for the introduction. Thank you to the organizers. As was introduced, my name is Michelle Kotyula. I'm at Rutgers. I work with Karen Rabe, and I'm going to be talking about ferroelectricity and samarium nickelate with intercalated hydrogen. So first, just to give you an idea of what hydrogen-doped samarium nickelate is compared to samarium nickelate, it's an electron-doped structure where you intercalate the hydrogen in a reversible process, and this is due to the fact that hydrogen-doped samarium nickelate is an ionic conductor. And through this process, you can actually dope at extremely high concentrations of electron onto the nickel. So when the hydrogen intercalates, the electron comes off the hydrogen, localizes on a nearby nickel, and you convert a nickel 3+ to a nickel 2+. So there are some cartoons in this talk, and when any of the octahedron become darker, it's because this is showing an extra localized electron. Experimentally, what you see is that you get a huge change in resistivity as you intercalate the hydrogen. So here we go through about 7 orders of magnitude change, and then once you take the film out of the hydrogen-rich environment and put it into oxygen, the hydrogen will reversibly come out. Along with the change in resistivity, you also see the sample become transparent. So you can see words behind now this picture. So I just want to point out, we've added more electrons to samarium nickelate through this process, and we've made it more insulating and transparent. So at low concentrations of hydrogen, can we use the position of the hydrogen and what happens to the local structure to create a polar structure from samarium nickelate, which is nonpolar, and can we make them switchable? I'd like to point out this is not the first time someone's looked at making a ferroelectric from an ionic conductor. So there were transitions in ionic conductors to ferroelectrics seen going back to the 80s. So the bulk of my talk, we're going to first talk about some pristine properties of samarium nickelate to situate ourselves, then the microscopic picture of electron doping, what happens to the electronic structure, and then moving on to when we look at the explicit hydrogen, how this changes and actually creates a polarization, and then how we can at least predict maybe a switchable state. These calculations are done in a pretty standard fashion using VASP. Because samarium nickelate has a PBNM or P21/N structure, you have a 20 atom unit cell with 4 nickel per cell. And this hydrogen dope structures we'll be looking at is 1 added hydrogen into this 4 nickel cell. So again, the main goal I want to get to in this talk is looking at a switchable polar state that is not only based on the inclusion of hydrogen into the lattice, but the fact that we have electron localization and an actual just purely electronic dipole in the structure. So some of you might be familiar with the family of rare earth nickelates. They have a very well-known metal insulator transition that occurs for all of them except for lanthanum nickelate. Going through this transition, the structure changes from PBNM to P21/N. At room temperature, which we have mostly studied this material, samarium nickelate is an insulator, but it doesn't show a large charge disproportionation. So this topic of charge disproportionation and the insulating structure is very well studied, maybe not very well agreed upon, but that's not what I'm going to be focusing on in this talk. So, as I said, the pristine samarium nickelate at room temperature and low temperature has a P21/N symmetry. This means that we have 2 inequivalent nickel sites in our 4 nickel unit cell. In this case, even though we have 2 inequivalent nickel sites, all the octahedral volume are equivalent, and there is a Jahn-Teller distortion. Because the nickel is in a D7 configuration, we end up with magnetic moments that are all equal and about 1 Bohr magneton. So representing my unit cell with 4 nickels in a slightly cartoon-ish scheme, I'm going to be showing also the occupied nickel EG electrons. So in the D7 configuration, you have 1 EG electron. So here this is showing the 2 different sublattices of the nickel, and they each have 1 EG electron in the pristine state. The accompanying electronic structure, we see a small gap, and this is occurring between the EG states of the nickel. We do see a very large hybridization with the oxygen states. So here I've colored in the remaining unoccupied nickel EG states. And so we see that for each sublattice, you have 3 then times 2 remaining EG states, and the remaining gray density of states you see around it is the part attributed to the oxygen. So as we add electrons, I'm first just going to add an electron with a positive background. This can be done in VASP just by increasing the number of electrons in the calculation. When this happens, we see a marked shift in the density of states, and the number of bands themselves are now different in this region right above the Fermi energy. So what's happening is this nickel now has an extra localized electron. This octahedron is about 13% larger, and we see the magnetic moment doubles. If we look at the associated density of states with this nickel, we see now there are only 2 unoccupied EG states, and there is this state that has moved from the conduction band below the Fermi energy. So the remaining density of states stays roughly the same. The slight splitting is due to the fact that we've broken some symmetries. But our overall gap hasn't changed. However, we can see the number of states in this conduction band has reduced in this intermediate doping state. So just to give you a quick summary of what happens if you fully dope samarium nickelate, in this undoped structure, we have this small gap. It has 4 bands, 1 for each nickel in our unit cell. And in that intermediate doping structure, the added electrons localize 1 at a time. 1 band from this conduction band is moved into the valence band. This is not a rigid shift as we're doping this. Finally, when we fully dope it, our old conduction band is completely occupied. It's moved into the valence band, and our new conduction band is really about 3 eV above the Fermi energy. And so what's happened is we've rearranged the bands and opened a new gap that gives us this very insulating state. So going towards adding explicit hydrogen into this structure. Because of the octahedral tilts present in the PBNM or P21/N structure, where you put the hydrogen really makes a difference. So here I'm showing you the low energy structure of the hydrogen. You see that it likes to sit in a tetrahedral space where the octahedra can't towards each other. If we compare this to just simply moving the hydrogen below to the tetrahedral space where the octahedra are now canted away from each other, we see that this is already 100 MeV higher in energy. Also, if we look at the inequivalent oxygen site along the c-axis, because there's an in-phase rotation along this axis, you don't end up with a tetrahedra. So you get a different space where the hydrogen is coordinated, and this becomes even higher in energy. So going forward, this is going to be the type of structure we focus on. So keeping this hydrogen in this area where the octahedra are canted toward each other. So as before, when we added an electron, we see that the added hydrogen provides this electron to the samarium nickelate. Now, instead of just a general positive background charge, we have pretty much a proton sitting right here in our structure. So the magnetic moment of this nickel is again doubled. We see a similar volume increase. However, before, the volume increase was quite uniform. There was nothing breaking the symmetry and distorting the octahedra. But I'll touch on this in a second. I'd also like to point out that the change in electronic structure is remarkably similar to just having an electron and a positive background charge. So if you care just about the electronic structure, the actual position of the interstitials is not so important. As I said, you get a very distorted octahedra due to the hydrogen that now is sitting next to it. So if we're now looking in the AB plane, so imagine looking from above, the hydrogen likes to be opposite to this long bond of this nickel-oxygen octahedra, which is present because of that Jahn-Teller distortion I mentioned earlier. So we can actually easily visualize this electron localization by comparing the charge densities of different calculations. And so we can see that there is an electron depletion around the hydrogen, and it accumulates on this nickel-oxygen octahedra neighboring it. So here I'm showing a contour plot that's along the 1-1-1 plane that pretty much cuts along this hydrogen-oxygen bond. So the electron is localizing on the nickel-oxygen octahedra. It's not just on the nickel alone. And we get a polar structure that is not just due to the position of the hydrogen. We also have an expansion of the associated nickel octahedra. And because of the electron localization on this, we have this charge-ordered structure now. So we have a purely electronic dipole as well that is roughly an electron times the bond length, the nickel-oxygen bond length. So we end up with an overall polarization of about 27 microcoulombs per centimeter squared. And it is not in a trivial direction. So I'm trying to orient you in the direction of the polarization. So it's going from the center of the octahedra towards the hydrogen. So we have this relatively large component along the c-axis, and then otherwise it kind of remains along the 1-1-0 direction. So how do we construct a switchable state? So as I said before, the hydrogen likes to remain opposite to the long axis of the nickel that has become nickel 2+. So here in this structure, I'm just showing the one layer that has the hydrogen in it. So in that case, half the nickel are nickel 3+, the other half are nickel 2+, because now this is in the next unit cell. So if we want to create a structure where we move the electron from this nickel to here, we have to switch the ordering of this long and short axis. So looks something like this. Now our other sublattice is nickel 2+. The one that originally had the electron is now nickel 3+. Unfortunately, if your AB plane is not cubic, there's a difference in energy between these two structures. So in relaxed samarium nickelate, this is around 100 MeV. So going forward, to make a switchable state, we're going to strain this to STO and have this cubic in AB plane. So making samarium nickelate films on STO or strain to STO in our calculations, we see they have a very similar relaxed c-axis. Even though these parabolas look like they have slightly different minima, they're pretty close. And the scale here is about 1 MeV. So if we have this orthorhombic structure, we can switch from one to the other by linearly interpolating the structures. It remains insulating throughout. We have an energy barrier that's a little high, about 200 MeV, and we can see clearly that the magnetic moment switches between the single electron, e.g. electron, and the double electron. So finally coming to the polarization, because the position of the hydrogen doesn't change, the direction of the polarization along this c-axis is relatively constant. However, in the 110 direction, it does flip. So we end up with a switchable polarization of about 23 microcoulombs per centimeter squared. So I'd like to come to my conclusions. So I've discussed how we can change the structure of SNO using added hydrogen, which causes electron doping, and the electrons actually localize on one nickel and are not itinerant in our structure. We've studied just one hydrogen added into a 4-nickel unit cell, and this gives us a polar structure, and we can have a switchable state with samarium nickelate with this intercalated hydrogen constrained in a cubic in-plane situation, constrained to the Laz parameter of STO. And this gave us a switchable state where the polarization remained along about the 110 direction of the PB&M cell, which is the 100 or 010 pseudocubic direction. So I'd like to thank you guys for your attention. I'd like to thank members of the Rabin Vanderbilt groups, especially Cyrus, who you're going to actually hear from in a few talks. And again, thank you for your attention and getting up so early.
Okay, questions?
So in your calculation, it looked like you used a G-type magnetic order.
Yep.
The nickelates exhibit an E-prime type.
Right.
Do you know the sensitivity of the polar structure or the charge order that you see on the magnetic order?
Yeah, there's... So first off, to get the E-type, you need a very large unit cell. So we looked in the 4-nickel unit cell, we looked at a whole bunch of different types of magnetic orderings. In terms of the electron doping and the changing of the band, overall like qualitative changing of the band structure, there's no difference. Once you get to fully doped structure, you see the same behavior, and when they do magnetic measurements of the fully doped structure, there is no long-range magnetic order. So in that case, we decided not to focus a lot on the magnetic order. I find in the calculations themselves, if you have, the nickel always wants to remain in this high state, high spin state due to the Hund's coupling, but then otherwise it tries to minimize its overall magnetic ordering. So if you have a G-type original ordering and you add now 2 electrons, it's going to try to put the electrons on nickel so that you still have an antiferromagnetic state. If you do this with A or C, you get a similar result.
Any other questions? So I have one question. So for this reversible hydrogen going in and out, I mean, what kind of temperature and pressure conditions do you need for that to happen?
So they can do this at room temperature. It just takes a little longer. Often experimentally, they do this around, I want to say like 100 Fahrenheit. So the metal insulator transition of samarium nickelate happens at around 104 Celsius. So they do this doping below that transition. So it will, but then once you've intercalated the hydrogen, it is stable in ambient conditions. Also, they've tuned, I think, the growing conditions for the samarium nickelate to have these films that exhibit a good metal insulator transition and are switchable. And I forgot to mention, so the experimental motivation and the group we've been working with on samarium nickelate generally is the Ramanathan group at Purdue.
Okay, so let's thank the speaker again. So next we have a presentation from Shu Liu from Carnegie Institution right here, and she will tell us about the origin of the negative longitudinal piezoelectric effect. There you go.
Great. Thank Ilya for the introduction, and also thank the organizer for the invitation. So in today's presentation, I will introduce and explain this negative longitudinal piezoelectric effect, which was considered as a real anomaly and didn't get that much attention. So in this talk, I will show you with both quantum mechanics calculations and material informatic methods that this is actually a quite common phenomena, and this work was carried out here at Carnegie, collaborated with Ron, and with funding support from Office Naval Research, Carnegie, European Research Council, and computational supports provided through HPC-MO. During my presentation, I will jump to a slightly different topic, but it's also highly relevant to this workshop. So for this audience, I probably don't need to speak too much about the importance of piezoelectric materials, which is truly a class of smart materials that can convert mechanical energy to electrical energy and vice versa, making them very useful in a lot of modern devices from sonar to MEMS nanogenerators and vibrational energy harvester. So the piezoelectricity is characterized by the piezoelectric coefficients. In this presentation, I will mainly focus on the longitudinal response, which is the response along the polar axis. There are two piezoelectric coefficients. One is E33, which relates the change in polarization to the change in strain. Another one is D33, which reflects the strain change in response to external electric field. And these two piezoelectric coefficients are related to each other through elastic compliance. Developing better piezoelectrics with larger D33 and E33 is active, ongoing research area, and there are a lot of good reasons for that. We sort of take it for granted that E33 and D33 are positive because for all the materials we care about or we have been studied have positive D33, but these two piezoelectric coefficients can be negative, and this is called a negative longitudinal piezoelectric effect. And this is a very counterintuitive phenomena because based on the definition, when we stretch the material, increasing the strain, the polarization actually becomes smaller. So equivalently, when we turn on electric field along the polar direction, even though the polarization becomes larger, the lattice constant becomes smaller, giving you a negative D33. So this is very counterintuitive. You may be wondering whether this ever been observed experimentally. Like 2 years ago, it turns out that this negative piezoelectric response was observed in this well-known ferroelectric polymer. So this is the structure for PVDF. The polarization comes from alignment of molecular dipoles, and we can switch this polymer by applying electric field. They measured the polarization electric field hysteresis loop and also the strain electric field hysteresis loop. As you can see here, when the magnitude of the polarization becomes smaller, the corresponding strain becomes larger. When they increase the polarization, the coupling strain becomes smaller. So this is a clear indicator of negative piezoelectric effect. In a paper, they attribute this negative piezoelectric response to the unique microstructures of PVDF polymers with intermixed crystalline phase and amorphous phase. So in other words, it's not intrinsic bark properties. So the question I would like to answer is, are there single-phase bark materials possessing this negative response, and how common are they? I looked into literatures. There were actually scattered reports. I think this paper was from David's group. They look at the piezoelectric coefficients for some 3,5 zinc blende semiconductors. As you can see, quite a few of them have, even though small, have negative E33, in this case along the 111 direction. It turns out Wurtzite boron nitride has pretty decent negative D33 in these two, reported in these two papers. So now the question is, what is the origin of this negative E33, and can we design piezoelectrics computationally? So I will start with the fundamentals of piezoelectricity from quantum mechanics. It is now well established that we can decompose the E33 into two terms. One is this clump ion term that is evaluated by fixing internal atomic coordinates. It reflects it is a purely electronic effect and reflects the change in polarization in response to microscopic strain. And it is very easy to show that if in a classic dipole moment picture, this term is 0, but in real case, we always have charge transfer, so this term is non-zero and is often negative. The second term is called internal strain term. It comes from the atomic relaxations in response to this macroscopic strain change. For most piezoelectric materials we have studied, this internal strain term is very positive and dominates over those negative clump ion terms, so therefore the total E33 are positive. But I think from this table we can see that at this fundamentally there's no physics preventing the realization of negative response, and this equation actually tells us a very general design principle, that is to find piezoelectric materials with small internal strain term. And as you can see, the internal strain term depends on the Bohr effect charges and also the atomic relaxations. So for piezoelectric materials with rigid potential energy surface, they're more likely to support a negative E33 and D33, and this is our general design principle. That is to find materials with rigid chemical bonds. I looked into literatures. One particular class of ferroelectric materials called hypertension. Again, it's from David's group. I think they talked about this work a couple years ago in this workshop. It is called ABC ferroelectrics. It's a hexagonal crystal, and it is not perovskite. And the nonpolar, you can really consider this nonpolar phase a layer structure with A, B, C stackering. And the polarization comes from the buckling of these BC layers. It caught my attention because in the paper, they also calculated the switching barriers. This figure shows which is essentially energy difference between the polar phase and non-polar phase. So this figure shows the switching barrier and energy difference as a function of polarization for all the ABC ferroelectrics they discovered with first principle high throughput approach. So as you can see, a lot of ABC ferroelectrics are quite rigid. They have very large switching barriers. So particularly for those compounds containing lithium atoms, and lead titanate, I think roughly the switching barriers, the barrier height is around like 0.2 electron volt per formula unit. So clearly, these ABC ferroelectrics are much more rigid than lead titanate. So I think they are very good candidates to start with. But now I'm going to jump to a slightly different topic because these ABC ferroelectrics are, I believe, they're a very robust platform that can enable many novel functional properties. It was proposed that some ABC ferroelectrics are hyperferroelectrics. I think it's a very interesting property that is a proper ferroelectrics with persistent polarization in the presence of depolarization field. So this is the photon spectrum for the nonpolar phase. As you can see, both the TO mode and LO mode are unstable. This is very different from like conventional proper ferroelectrics such as lead titanate, barium titanate. We know that only the TO mode is unstable in the nonpolar phase. The consequence of this unstable LO mode is that hyperferroelectrics can be polar even under ideal open circuit conditions. So in this paper, I think this figure illustrates the difference. For normal ferroelectrics, this is the polarization as a function of displacement field. As you can see, this line crossed the zero point. So what's happening is when you put a slab of ferroelectric material in vacuum, because of the depolarization field, coming from the surface charges, it will kill the ferroelectricity. So under this very ideal open circuit condition, ferroelectric thin film will be, will be non-polar. I think this is now well established. In contrast, for hyperferroelectrics, when you put a slab of hyperferroelectric in vacuum, they can still be polar. And so this really demonstrates the robust ferroelectricity supported by ABC ferroelectrics. I think we decided to look at the charged domain walls in hyperferroelectrics. In yesterday's presentations, we learned that charged domain walls are actually very rare because of this very strong depolarization field. So whenever we have this a pair of head-to-head and tail-to-tail domain walls, we have positive polarization bound charge at head-to-head domain wall and negative polarization bound charge and tail-to-tail domain wall. This creates a huge depolarization field, which will kill the ferroelectricity. And this is indeed the case for conventional ferroelectrics like lead titanate. So even in a computer, essentially at 0 Kelvin, we can start with a configuration with charged domain walls. But during relaxation, it will spontaneously transform to these single domain configurations because this configuration is not even metal stable. So we carried out first principle density functional theory calculations in lithium, beryllium, antimony, and this is a hyperferroelectric. So this is a supercell. It has one head-to-head domain wall in the middle of the supercell and a tail-to-tail domain wall at a boundary. What I show here is the atomic displacements and also the polarization across the supercell. As you can see, it clearly has this well-defined anti-parallel 180-degree charged domain walls. So this really comes from this hyperferroelectricity, the persistent polarization in the presence of very strong depolarization field. So what's surprising is if you look at the polarization in this bark-like region, away from the head-to-head domain wall, you can see the polarization value is very close to the single domain value. So we further look at the electronic structures of charged domain walls. So what's happening is the presence of charged domain walls close the band gap. You may think the system is metallic. Well, you may say it's a polar metal, but what's happening is from the layer resolved density of states, we can see that we have quasi-two-dimensional localized electrons at head-to-head domain wall and also quasi-two-dimensional whole gas localized at tail-to-tail domain wall. So these free carriers almost compensate the polarization bound charge perfectly, therefore screen the depolarization field. We further calculate the electrical conductivity for the single in single domain, also for the supercell with charged domain walls. As expected, along the domain wall, within the plane of the domain wall, the electrical conductivity it has metallic signature, but perpendicular to the domain wall, that is across the supercell, the conductivity is still very low. So we think many hyperferroelectrics, in this case lithium, beryllium, antimony, are potentially really ideal candidates to study high-density charged domain walls. They may also have potential device applications because of this quasi-two-dimensional electron and whole gas. Okay. So now I'm going back to the piezoelectric properties of ABC ferroelectrics. So we calculate the piezoelectric coefficients with a density functional perturbation theory. The protocol is pretty standard. All the calculations are carried out with local density approximation with GBRV superpotential. We use very high energy cutoff, around 60 Rydberg. As you can tell from the table, quite a few ABC ferroelectrics have negative E33 and D33. I just want to highlight two compounds. For these two ferroelectrics, they have very decent E33 and D33. They are comparable with zinc oxide prototypical piezoelectric materials. We also evaluate the piezoelectric coefficients with finite difference method, which I think is probably much more intuitive than density functional perturbation theory. These are the results for lithium beryllium antimony. What I did is to look at the polarization as a function of uniaxial stress and also the polarization as a function of uniaxial strain. With two density functional, they essentially give the same results. The slope tells us the piezoelectric coefficients. So I think this figure is probably more intuitive. So when we stretch the material, that is apply a positive uniaxial strain, the polarization becomes smaller. When we apply a compressive strain with negative strain values, the polarization becomes larger. So it is indeed consistent with the idea of a negative longitudinal piezoelectric response, as I showed earlier. So we also look at the strain change in response to external electric field with finite field method. It's a little bit challenging to get it converged, but at the end we get this nice linear relationship between the strain and the external electric field. As you can see, when we apply the positive electric field along the polar axis, the strain becomes smaller. Again, consistent with the picture of negative piezoelectric response. So we further look at the polarization reversal process in this compound with variable cell largely elastic band method. So what I show here is the polarization reversal, the switching barrier, while this is the zero field case. So the barrier is high, as we will expect from the very high barrier in the double well potential. And through the switching, all the structure remains to be insulating. And you can, if you look at this intermediate region, when the polarization becomes smaller, the C-axis actually becomes larger. And when the polarization becomes larger, the magnitude of the polarization becomes larger, the C-axis shrinks, contracts. So again, all different methods, all different computational methods are consistent with each other, really demonstrating the presence of negative longitudinal piezoelectric effect. So the origin of this negative response really comes from this negative clamp ion term. So as you can see from the table, for these two compounds, they have negative clamp ion, the same as lactinate, but they have very small, nearly zero internal strain term. However, in lactinate, this internal strain term dominates. So because of this very small internal strain term, these two ABC ferroelectrics have negative E33. We also look at the buoyant free charges and also the atomic relaxation in response to the macroscopic strain. As expected, these ABC ferroelectrics have pretty small buoyant free charges, and it doesn't move that much in response to the external strain. So I think this is very clear to us that now it's very clear to us now that the origin of this unusual piezoelectric response relies on the small effective charges and also the rigid potential energy surface. Then the question is how many compounds we can find. The good thing is back in 2015, there's already a first principle based database of piezoelectrics with their E33 calculated with density functional perturbation theory. And these compounds, this is the open source, well-curated data we can access from Material Project. And this database contains nearly 1,000 inorganic compounds. So with just 2 lines, we quickly identify nearly 100 inorganic crystalline compound with E33 smaller than -1 coulomb per meter square. So this really demonstrates that this phenomena is much common than we thought. Here I just highlight a few examples. So this is sodium oxide. It's kind of surprising that I look in the literature. This seems to be some kind of high pressure phases. It has a pretty large negative E33. It's minus 9.6 coulomb per meter square. Probably a more detailed quantum mechanics calculations is worthwhile. And this layer structure also has very negative E33, minus 7.4 coulomb per meter square. And these two compounds have already been synthesized. They're non-compounds. They have pretty decent E33 and negative E33 as well. But as you can see, they're not perovskite structures. So, okay. So a natural consequence of negative piezoelectric response is the pressure-enhanced ferroelectricity. So this gives a very general explanation. So delta P3 is the pressure-induced polarization change. Because now we need to consider the effect from volume change, so we need to use this improper piezoelectric coefficients. So the strain change is negative. For normal ferroelectrics, because of this very positive E33 term, the polarization change is negative. However, for ferroelectric with negative piezoelectric coefficient, this will result in polarization enhancement. And this is indeed what we observed based on our DFT calculations. What I show here is the polarization change as a function of hydrostatic pressure. As you can see, a lot of them, particularly for ABC ferroelectrics with negative E33, they have polarization increasing with increasing hydrostatic pressure. So this makes them very appealing for high-pressure applications. I also would like to put our work in a bigger context. In the literatures, people talk about pressure-enhanced ferroelectricity from time to time. I believe a lot of you are familiar with this work that is lattining. So in this paper, it was suggested or proposed. It was claimed that the ferroelectricity will reappear above some critical pressure. Maybe Ron has some new update, but it's clear that when we apply the hydrostatic pressure, the polarization will become smaller. In this paper, they show that for some improper ferroelectrics, rare earths, ferrite, the polarization will also increase with increasing hydrostatic pressure. But in this case, it is because of zone boundary mode. However, for ABC ferroelectrics, it's a proper ferroelectrics characterized by a zone center mode. So in this paper, they also look at polar instability for some geometric ferroelectrics. Indeed, for some geometric ferroelectrics, so what I calculate is the square of the TO mode frequency as a function of pressure. This is essentially pressure. This is the high pressure region. As you can see, the polar instability indeed get enhanced with increasing pressure. So within this picture, I think ABC ferroelectrics are probably better characterized as geometric ferroelectrics. This the last slide. So it turns out that for some ABC ferroelectrics, the polarization is extremely robust. So what I show here is the polarization as a function of hydrostatic pressure all the way up to 80 gigapascal. And the red line is the polarization. As you can see, it keeps increasing. Around 80 gigapascal, the band gap closes. So it is not because because the structure is metallic, we cannot define the polarization. And this is the band structure. Indeed, at 85 gigapascal, there are some bands across the Fermi level. But what's surprising is even at this very high pressure, 85 gigapascal, the structure remains to be in a polar space group. So we look at a phonon spectrum, and all the phonon branches are stable. So that's why I call this like a high pressure polar semi-metal. Okay, with this, I would like to conclude my presentation with detailed quantum mechanics calculations, also material informatic methods. We really demonstrate that this negative longitudinal piezoelectric effect is a common phenomenon. We really hope that this work can inspire some more experimental studies. And thank you for your attention. I'm happy to take any questions you have.
All right. Questions?
I have two short questions. First, is there any, do you also see a negative dielectric constant? Second is there any real application for this material?
Negative dielectric constant, we don't see negative dielectric constant. When we turn on electric field, the polarization still becomes larger. The strain becomes smaller. So the dielectric constant is still positive.
So the coupling between dielectric constant and piezoelectric constant, there is a negative sign, right? It's also negative in this case. Right? Because your PVDF actually shows a positive dielectric constant, but it has a negative piezo constant. In your PVDF example,
yes,
you showed the hysteresis curve, but your strain curve is kind of abnormal. So that relationship. The dielectric constant, if my understanding is just dP over dE, right? When you turn on electric field, the polarization still becomes larger. So the dielectric constant is still positive. What I mean is, your dielectric constant usually has a linear correlation with your piezoelectric constant. History. It's a well-known relationship. So you are suggesting there should be a negative sign. Am I right?
No.
Right.
Right.
Oh, okay.
Okay, good. So the second question is whether there's real experimental, real applications. Well, it's hard to tell. The physics is definitely very interesting, but we thought about what would happen if you put a conventional piezoelectric and material with this negative response, and when we turn on electric field, part of the material want to expand, part of the material want to shrink. That may have some interesting physics at interface or interesting applications. So that's why we really hope that this work can inspire more experimental studies. Yeah.
Okay, thank you.
Compliments for this really nice study.
Thank you.
You had a throwaway remark which puzzled me slightly. You had potassium iodate, and you said it's not perovskite. Now, are you talking about a completely new phase? I mean, the classic potassium iodate is well known. It's not trigonal, it's monoclinic. And it has, it's one of these things which is ferroelectric and not ferroelectric. Or are you talking about a new compound you discovered?
Oh, this, okay. So that's I just simply take it from a database. So you're talking about this compound, right?
No.
Potassium iodate?
Potassium iodate is a perovskite. It's not that, it doesn't look like that.
Well,
I saw the structure. It's not.
So this is ICSD code. So I haven't looked at the papers, how they synthesize this compound, but
I think somebody needs to go through the database there.
Well, that's always a concern. A word of caution. These are results of high throughput application. I believe they are calculations, but if you really want to go to lab to synthesize, maybe it's better to first do a very careful, more accurate DFT calculations.
You can just look into the original papers.
Yeah, ICSD. So this is ICSD code.
I just wanted to go back to your band structure. You showed the band structure for a single domain.
Which band structure? It was electronic band structure?
Yeah, that's right.
Okay, the chart domain wall part. Okay.
Yes. So you showed it just with a single domain, and then you added in the domain wall.
Yes.
It's become basically metallic. That's what it looks like.
Wow. Yes.
But my question is that band structure a 2D sort of band structure projected onto the domain wall, or is it?
Oh, this is just a whole.
It's the average of the slab.
Yeah, this is the whole Brillouin zone, but it's much better to look at the layer resolved density state. So if you look at the bark-like region, it's still insulating. So, but here it's metallic. Well, at least you have quasi two-dimensional electron gap.
Yeah, because you write gamma, M, and K, so it's bulk. It's 3D.
Yeah.
Okay? So that means that the domain wall has made your whole slab metallic.
Well,
from the band structure, not from the density of states, from that band structure.
Right.
Yeah.
The speaker. So our next talk is by Cyrus Dreyer, also from Rutgers. and Cyrus will tell us about current density implementation for calculating flex electric coefficients.
Thanks for the introduction. This work was done in collaboration with David Vanderbilt and also Max Stengel from Barcelona. So we just heard a lot about piezoelectricity. I'll just remind you what flexoelectricity is. So flexoelectricity is polarization that's induced by a strain gradient as opposed to a uniform strain. And you could apply a strain gradient to a material by, for example, bending it or some non-uniform compression. So we're interested in flexoelectricity for a couple of reasons. One of them is the possibility for novel device designs, for example, piezoelectric type transducers with non-piezoelectric materials. Also, large strain gradients can be present in nanostructures unintentionally, for example, at heterostructure interfaces, and therefore the flexoelectric effect could play a large role in the properties of such devices. So from an atomic point of view, the flexoelectric effect is pretty intuitive. We apply a strain gradient, for example, by varying the x strain with x position. Then we create a non-symmetric environment, in this case in the x direction, and therefore we will induce dipole moments in the charge density and non-zero polarization. So the way that we discuss the flexoelectric effect, just like the piezoelectric effect, is through these flexoelectric coefficients that relate the polarization, for example, in this case in the x direction, to linear order to the strain gradient. So in our example of a longitudinal type strain gradient, also in the x direction, all of the four indices of the flexoelectric coefficient are the same. Of course, we could have a variety of different types of strain gradients, including shear and transverse, and then also longitudinal. And so a general flexoelectric coefficient will look kind of like this. So our goal is to calculate all of the flexoelectric coefficients for a given material from first principles density functional theory calculations. And so if you've been coming to this meeting for a while, you've probably seen presentations of some previous work calculating flexoelectric coefficients, both from David's group and also Max Stengel. So I won't go into any of the details of these two implementations. They have a lot of interesting differences. But one thing that they share is the fact that they require calculations of large supercells in order to access all of the flexoelectric coefficients. And this is computationally intensive, especially if we want to calculate these coefficients for a variety of materials with a variety of symmetries. So we would like to calculate the flexoelectric coefficient from a single unit cell calculation, just like the density functional perturbation theory implementation to calculate piezoelectric coefficients that we heard about in the last talk. So in this talk, I'll just go over briefly our approach for calculating the flexoelectric coefficients from first principles using density functional perturbation theory on a single unit cell. And then at the end, I'll give some examples of our calculations for cubic oxides. So the first question that we have to answer is, how do we model a strain gradient in a bulk material? It's not even obvious, since we've broken the translational symmetry of our crystal with a strain gradient, how to define a unit cell. So the approach to doing this is to realize that we can identify the different types of strain gradients in different types of acoustic phonons. And so if we treat a strain gradient as a very long wavelength acoustic phonon, then we've recovered the periodicity that's necessary to do a bulk calculation. Of course, we don't want to try to create a supercell that will capture this long wavelength periodicity, but thankfully we don't have to. Using some well-developed methodologies in density functional perturbation theory, we know that we can describe the atomic displacements of sublattice kappa as a result of a phonon with a cell periodic part modulated by a phase with wave vector q. And in the linear regime, we can also describe responses to these atomic displacements, such as the polarization response, also as a cell periodic response modulated by a wave vector, the same wave vector q. And so if we're smart about factoring out these phases, we can just focus on the cell periodic parts of these, this displacement and response, and therefore only do calculations on a single unit cell. So in these schematics, these dots could correspond to a single atom in a unit cell, or they could correspond to a unit cell themselves, which in a general crystal may have several atoms. So this was touched upon in the previous talk, that in that case, you have two contributions. You have a frozen ion contribution, or in the previous talk, a clamped ion contribution, which is, again, the purely electronic response to the strain gradient. And then you also have a lattice-mediated contribution from the internal relaxations caused by the local strain and strain gradients. So in this talk, I'll be focusing on the frozen or clamped ion contribution. If you're interested in discussion about the lattice-mediated part, then I'll refer you to these references. So just briefly, the way that we calculate the frozen ion flexoelectric coefficient is by calculating this cell periodic polarization response that I mentioned before, and taking its second derivative with respect to phonon wave vector. So this would be a calculation for a given phonon with wave vector q, and then we take the second derivative in the long wavelength, or q equals 0 limit. So that's how we describe a strain gradient. The second question is, how do we calculate this polarization response that I've been referring to? So kind of in the schematics that I showed before, they were based on looking at the induced charge density from a strain gradient perturbation, or a phonon perturbation. And the induced charge density from a phonon perturbation is something that's readily available in most DFT packages, and it's been used on previous implementations to calculate flexoelectric coefficients. Unfortunately, we see that since the charge density is given by the divergence of the polarization, it only contains information about the longitudinal components of the polarization field. And therefore, from the charge density in bulk, we can only calculate the longitudinal flexoelectric coefficients. If we want to calculate the full flexoelectric tensor from a bulk calculation, then we need to instead consider the current density that's induced by a time-dependent motion of atoms, which we know from electrodynamics is related to the polarization in the following way. So this current density is not something that is normally implemented in density functional theory, and so we have to develop our own methodology for these calculations. So in the next few slides, I'll just briefly touch on a few aspects of this methodology. So if we want to calculate the current density, we can start from the basic definition of current density in quantum mechanics. So we know that current density is defined by the continuity condition, which just specifies that if the charge density changes, then a current has to flow. If we combine this with the time-dependent Schrodinger equation, we get this familiar form of the microscopic quantum mechanical current density, which depends on these derivatives, spatial derivatives of the wave functions. So this is all kind of textbook material. However, it turns out that in the context of density functional theory, this current density is problematic for our purposes. And the reason is because of the ways that we describe the core electrons in a density functional theory calculation. So to make our calculations computationally tractable, what we do is we, in a cutoff radius, RC, around the atomic nuclei, we treat the wave functions and potential as kind of smoothed versions of the full all-electron wave functions and potentials, so-called pseudopotentials. And for some technical reasons that I won't get into right now, almost all modern pseudopotential implementations involve non-local operators in the potential operator. So if you apply to a wave function, you have a local operator and then a non-local operator that is in the form of this projector, in this case over angular momentum channels. And so these non-local operators cause a lot of problems for a physical interpretation of current density. The reason is if you apply a non-local operator to a wave function, you can have these unphysical and discontinuous motions of charges where charge can kind of teleport to different places within the cutoff radius. And so this kind of charge teleportation is allowed in Star Trek, but it's not allowed in physics. And so what we have to do is to make sure that when we define a current density, that it still satisfies the continuity equation even with the possibility of these teleportations. So it turns out that this definition of the current density actually does not satisfy the continuity equation when these non-local potentials are present. And so we need an alternative definition of current density in this case. So the way that we obtain this alternative definition is, again, from classical electrodynamics. We know that we can write the energy stored in a magnetic field in the following way, and we can relate this to a product between a vector potential and the current density. So here we have a relation between the current density and the energy, and so we can use that to develop a quantum mechanical operator, a current density operator, that is the derivative of the Hamiltonian in the presence of a vector potential, which will describe our phonon perturbation, the derivative with respect to the vector potential. And so I won't go into any details of how we actually calculate this. You could ask me after the talk. But this definition of the current density actually satisfies the continuity equation and gives a physically meaningful value for the current. So the induced polarization is something like a matrix element with this current density operator. We still have the fact that our atomic motion is time-dependent, and therefore these wave functions are time-dependent. And the fully time-dependent wave function is also not something that's readily available in density functional theory. So the second question would be, how do we treat this time dependence? And the way that we do that is if we, again, start from a pristine crystal, and then we slowly move the atoms to create this strain gradient, then we can write the fully time-dependent wave function, parameterized by this time-dependent atomic motion lambda, as an expansion, the sum of the static wave functions at a given lambda, plus the first-order adiabatic wave functions, so first order in the velocity of the atoms. And again, I won't go into too much detail, but it turns out that these first-order adiabatic wave functions can be calculated using quantities that are used, for example, in a static phonon calculation, specifically the first-order Hamiltonian. So using this adiabatic expansion and our alternative definition of the current operator, then we can calculate the induced polarization that we need for the flexoelectric coefficients. So just in the last few minutes, I'll just give some simple examples of these calculations. So I'll calculate frozen ion coefficients for very simple material, cubic strontium titanate. For this symmetry, we have three non-zero flexoelectric coefficients, a longitudinal, shear, and transverse coefficient. And again, I'll remind you that we calculate these flexoelectric coefficients by taking the second derivative of the polarization with respect to Q. So this is an example of a calculation. We have induced polarization versus Q. We can take the second derivative of these curves, this polarization in the x and the y direction, and therefore obtain the clamped ion flexoelectric coefficients. So compared with previous calculations, which are highlighted in blue, we have very good agreement. But of course, I'll remind you that these new calculations were calculated on a single unit cell and didn't require the computationally intensive supercells of the previous calculations. And because of this, we can perform calculations on a large number of materials. Here I just show other perovskite oxides all in the cubic phase, and then a slightly different material, magnesium oxide. And we can calculate, again, not just the longitudinal, but also transverse and shear coefficients very efficiently. So just to conclude, I've given you a brief overview of our approach for calculating the frozen ion flexoelectric coefficients by modeling strain gradients along wavelength acoustic phonon and calculating the current density response, and then given some examples of cubic oxides. Thank you.
Okay. Rafael?
In the simplest case of piezoelectricity, one distinguishes carefully between polarization in zero field, polarization in depolarization field, open circuit, short circuits. Like now here in flexoelectricity, everything is very complicated. You cannot think in terms of zero field or whatever. For instance, if you compute mu x, you always have the polarization field. Now, I remember of a very elegant paper by Max Stengel on change of the metric and the like, but I don't see well how this comes into these Q derivatives. So where is the field hidden in those Q derivatives?
Yeah, great question. So I didn't go into this, but there will be, in principle, if you're not careful, there'll be discontinuities of the polarization at Q equals 0 due exactly to this electrostatic boundary condition problem. So in our calculations, what we do is we, in the calculations I've shown, we enforce short circuit boundary conditions by, in reciprocal space, these reciprocal space derivatives, removing the G equals 0 term in the electrostatic potential. Yeah, so exactly. So maybe a physical picture of how we remove this by removing the G equals 0 term in the first order potential is similar to having, in the case of piezoelectricity, the argument of having a kind of a diffuse, free charge that screens the long-range electric fields. So it is taken into account, and as you said, the metric implementation, which we're working on, so it also kind of treats this.
So have you found any surprising materials with large coefficients?
Yeah, so that's kind of the next step. I think now that we have a methodology that we've seen in kind of the materials that we've studied before works well and is efficient, especially for materials of different types of symmetries. That's kind of the next step, to combine it with the lattice-mediated part and to start searching for interesting materials.
Thank the speaker. So last talk of the session is by Kyohei Takaya. I apologize if I mispronounce the name. And from University of Tokyo, and he will tell us about antiferroelectricity in a simple molecular model controlled by frustration between steric and dipolar interactions.
Thank you, Chair. Does it work? No. Okay. First, I'd like to thank the organizers for giving me an opportunity to talk here. My name is Kyohei Takai from University of Tokyo, Japan. So before starting, we are soft matter physics group, mainly studying spatial temporal heterogeneity in liquid gases and soft matter, for example, polymers, corrosion, etc. So today I'd like to present our viewpoints, soft matter physicist viewpoints on antiferroelectrics. So our question, maybe I don't need the introduction on ferroelectrics and antiferroelectrics. So one of the main differences in the polarization response and the external field. So, but my question is, what is the key factor to realize the antiferroelectric phase, and how the phase transition can be controlled? So there are some way to control the antiferroelectric phase. So maybe this is one good example of the bismuth ferrite, and under some modification in the left panel, the size of the substitution of the bismuth atom by some atoms with very different size exhibit antiferroelectricity in some region. But in right panel, the substitution by lanthanum does not yield antiferroelectricity. So this is changing the Goldschmidt tolerance factor, and for left panel, the antiferroelectric phase emerges. And another way to control the antiferroelectric phase is to apply pitaxial strain. So both experiments and numerical computational numerical calculation shows that the antiferroelectric phase is in red zirconate. The compressive strain stabilizes ferroelectricity, and the tensile strain stabilizes antiferroelectricity. And these are the examples of inorganic substances, but the effect of modification can also be found for organic compounds by some modification. I don't explain detail, but it can be shown that the antiferroelectric phase is realized by some modification, and it's also found in magnetism. So thus, the phase behavior can be controlled by mechanical parameters. Mechanical parameters, I mean atomic radius, molecular shape, and external stress. But as long as I know, to our knowledge, there is no simple physical model that can explain such controllability of ferroelectricity and antiferroelectricity. So today, we report a new molecular model which captures essence of the phase behavior, including cross-coupling between polarization and strain. And for this purpose, I will show you that the point dipole and particle shape is sufficient. So for the point dipole model, this is developed in liquid theory. That this is called a Stockmeyer model, having the pair Lennard-Jones interaction and the point dipole electrostatic interaction. And this model is known to exhibit ferroelectricity in solid in this paper. But please recall that the dipole interaction for point dipoles are highly anisotropic. So anisotropic, I mean its sign depends on the relative positions, which can be controlled by varying particle shape, as in this figure. So suppose we have ferroelectric states, the dipole moment aligns in all the same direction. That in vertical direction, the dipole moment is repulsive, and in horizontal direction is repulsive, and the vertical direction is attractive. And by changing particle shape or applying stress, we can expect to change or control the attractive force between the dipoles, like in the right figure. So the idea is the coupling between polarization and strain. Yeah, this is our model of classical molecular model, and we modify slightly the Lennard-Jones pair interaction to include the particle anisotropy, shape anisotropy. And the detail is not important, but the important point is we can control the shape of the particle by one parameter, eta, in the second line. And also we take into account the electrostatic interactions. And this model is, we propose this model in this paper to study relaxar glassy behavior, but this is another story. Okay, so numerical method is we solve this model in classical molecular dynamics simulation. Classical molecular dynamics means the position is particle position is obtained by integrating the Newton's equation of motion, and the particle orientation is obtained by solving the Euler's equation. And the pressure is for some experts, I like to explain the temperature and pressure tensor are fixed, and the periodic boundary condition is applied and by smooth particle Ebert method. And important point is we ignore depolarization effect field by assuming that the sample is surrounded by a metal wall. So by this assumption, the no domain wall exists in equilibrium, and we can study the bulk property of the ferroelectrics. So I present the numerical result. So this is a phase diagram of our model. So this is a most important figure in my talk. So by changing the particle entropy eta changing eta corresponds to changing the particle shape and changing temperature. So there are three crystalline phases. One is paraelectric, and ferroelectric, and antiferroelectric. So in paraelectric phase, the particles form crystalline, but the orientation is disordered. So, sorry, I forgot to explain, but the orientation of the dipole moment is parallel to the long axis of the molecule. And in paraelectric state, the particle orientation is completely random in XTC or HCP configuration. So in this model, in paraelectric phase, XTC and HCP has almost the same probability. And for small anisotropy decreasing temperature, the orientational ordering occurs at some temperature, at certain temperature, to form ferroelectric phase in the left one. The crystalline phase is slightly deformed from mother FCC or HCP phase. But for very large anisotropy in the right part, the completely different phase emerges to yield antiferroelectric phase. So this is schematically written in the middle one, that the dipole moment aligns in anti-parallel manner to adjacent particles to decrease the potential electrostatic energy. So the crystalline phase is completely different. Okay, I will explain later. And this is a snapshot of each phase, ferroelectric and antiferroelectric phase. So this snapshot is obtained by gradually cooling the paraelectric mother phase. And for left one, the color represents the dipolar orientation, and almost all the dipoles are in parallel, yielding the ferroelectric phase. And in the right panel, there are some ferroelectric ordering in plane, in hexagonal plane, but the stacking of the hexagonal plane is in anti-parallel manner. So the crystalline structure of this antiferroelectric phase is listed, displayed here. So for paraelectric and ferroelectric phase, the stacking of hexagonal plane is the closest packing in two dimensions. So the stacking of hexagonal plane is the closest packing in 3 dimensions. But in antiferroelectric phase, the stacking is in different manner from both ferroelectric and paraelectric phase. So it's not a standard ABC or ABAB packing to yield FCC or HCP. The position of the anti-parallel dipole moment is in midpoint of the adjacent plane. So in this phase, the crystalline structure can be examined, and we found this state is in monoclinic. So, and to confirm this state is really antiferroelectric, we examined the field response to external field, and this is displayed in right panel and red line. So the double hysteresis characteristic to the antiferroelectric phase is obtained. So it's because under strong field, the antiferroelectric phase transforms into ferroelectric one. And this, because our model particle is anisotropic, like spheroid, so the transformation induces very large strain in blue line. And maybe an interesting result is in right panel, the frequency dependence of the response. So for lower frequencies in blue line is the antiferroelectric double hysteresis response, but for higher frequencies, there is not enough time to transform from ferroelectric to antiferroelectric phase, and the response exhibits single hysteresis curved characteristics to the ferroelectric phase. Okay, so because since in our model the strong electromechanical coupling exists, we can expect that this is not a result, this is schematic picture. So we can expect that the phase, ferroelectric phase and antiferroelectric phase can be controlled by external stress. So again, suppose we have the ferroelectric phase and the stretch in this direction, the particle relative distance, relative position of the dipoles changed, and for this stretching case, the antiferroelectric phase will be emerged. So this is one example of the mechanical switching. That first we prepare antiferroelectric phase in equilibrium and apply external stress in some directions, and we found that in some case in the top case the antiferroelectric to another antiferroelectric case with different particle orientation is realized. And in another case, the antiferroelectric to ferroelectric, the case transformation, and in third case, the antiferroelectric to paraelectric case transformation is found. So this will imply the interesting possibility of the controlling phase by mechanical stress. And finally, I show the electrocaloric effect by switching off the electric field and examine how the temperature changes. So this is a result of and in the left panel, first we prepare the ferroelectric state under strong external field at certain temperature, 0.65 in the figure. And when we switch off the field, electric field, first the temperature decreases because the potential energy increases due to the cutting off the potential energy coupled to the linear coupling term of the polarization and external field. But after switching off the field, the ferroelectric state transforms into antiferroelectric state, and the temperature increases to, in the figure, about 0.7. So this is a consequence. This is because the antiferroelectric phase has very lower entropy than the ferroelectric phase, and this can be clearly seen in the dynamic structure factor. This dynamic structure factor is calculated by calculating only the rotational fluctuation, not take the translational motion in account. And we confirmed there is little difference in translational motion. And difference in entropy between ferroelectric and anti-ferroelectric phase largely comes from the difference in the rotational vibration. So, yeah. So in summary, we propose the molecular model, maybe not a toy model, but anyway, we propose the molecular model exhibiting ferroelectric and anti-ferroelectric phase transition. And the important point is the competition or interplay between the steric interaction and dipolar interaction leading to the interesting phase diagram and mechanical switching and electrocaloric effect. Thank you for your attention.
Thank you.
You told it at the beginning, but I've missed it. So
sorry.
One other competing parameter, I would say, the moment of inertia of the moment of inertia of your particles.
Okay.
And so you have shown as a function of eta, but
okay.
I think that your particles do have a mass, I guess, and also a moment of inertia.
Yes.
Would be essential.
Yes, of course, but
so it does scale like, let's say, dipole over moment of inertia is something like that, how they scale, in a sense.
Okay. So this is just one example using anti-ferroelectric phase. So the mass of the particle is the scale unit. So it's set to unity in numerical simulation. And the moment of inertia is calculated by assuming this particle is spheroids. Corresponding spheroids.
Yes, but suppose you double the dipole moment, and you double the moment of inertia, you get the same results or not?
Yeah, very different. So this the magnitude of dipole moment is chosen so that the three-phase paraelectric, ferroelectric, and anti-ferroelectric phase is are realized in numerical simulation. So okay.
Okay. Any other questions? Okay, so let's thank the speaker and all other speakers.
Thank you. Thank you.